These pages contain the verification and adjustment procedures from the PM3217 service manual, and with some minor variations they seem to apply very well to the PM3214. Initially there are a few tables etc. giving a summary of all the adjustments and tests to be carried out. Ahead of the start of the detailed description for each test. There are these very helpful circuit board layout diagrams that give the locations of all the trim pots etc. that may need to be adjusted. It seems the major difference between the PM3214 and the PM3217 is that the latter has the circuit that drives the Y deflection plates of the CRT, described as the final amplifier, on a separate circuit board. Its layout is shown here. The PM3214 uses a simpler version of this circuit with fewer adjustments, and it's located in the corner of the main circuit board up here. I began working my way through these procedures, and all went well, only needed to make fairly minor adjustments in most cases. However, encountered a problem at this point. This procedure here described normal stroke invert balance for channel B. This involves adjusting trim pot R647 to make sure that the horizontal reference point of trace B does not shift when the invert function is enabled. The invert function is turned on for channel B by pulling out the vertical position control. Not surprisingly, while making this adjustment, it was necessary to switch the invert function on and off a number of times, and during that process, the switch suddenly failed. I'd imagine its internal springs have become disarranged, as happened previously to one of the other controls. That's very annoying, so now I'm going to have to completely dismantle that whole front control assembly again and try to put that right. However, I believe the adjustment had been made more or less correctly, and the switch had failed with the invert switched off. So I carried on and worked my way through almost all of the procedures. I left out a few towards the end. However, from that, I'm happy that this oscilloscope is in good working order. There are a few tests near the end that refer to applying a 50 MHz test signal, and I think setting the time base to 0.1 microseconds per division. The fastest time-based setting on the PM3214 is 0.2 microseconds per division, so I suggest using that and a 25 MHz test signal instead. After repairing that switch, I've refitted the front panel control subchassis, etc. When I opened the switch, the springs didn't appear to have come out of place, so I'm not sure why it has stopped working. Though I noticed that the small grey plastic piece that retains one end of each of the springs and pushes onto the shaft of the potentiometer had a small crack in it, so perhaps that was preventing it from moving up and down. I found the same problem in the other two that I'd previously reassembled, and in all cases I added a blob of glue to hold it in place, so hopefully that will solve the problem for good. There's one more of these controls of the same type that I've not opened yet, and I have a horrible fear that we all know what might happen soon. The remaining one is the trigger slope control for the delayed time base. Unfortunately, this is a control that probably won't be used very often. I now want to turn my attention to the mains transformer, which is mounted here on the rear panel. Here are the various parts. They're as shown on the circuit diagram. There's a filter capacitor connected directly across the mains, this large green thing here. And this rotary switch connects the neutral to one of various combinations of primary windings to allow operation from different mains voltages. There are two secondary windings, and they're wired in parallel. These windings appear here and here, and these two brown leads run off to the power supply board on the back of the oscilloscope. As I pointed out in part 1, the thermal fuse, which is fitted here, measures open circuit. However, I'm going to temporarily connect a jumper wire across the thermal fuse and then take some DC resistance measurements. I'll switch the meter to manual ranging, as the inductance of the winding sometimes upsets the auto ranging. The switch is set to 240 volt operation, and let's check the resistance between live and neutral at the plug. The pins are very grimy, so I might not be getting a good contact. Doesn't look so good. Measuring open circuit. Hang on. Let's press the probe through the dirt on the pins. I can't get a consistent reading, but certainly it seems the winding is not open circuit and not completely short circuit. Let's also check the resistance of the two secondary windings in parallel. This should be quite low. It is certainly not open circuit. I think there's a good chance this transformer's in working order. The problem is simply the failed fuse. I'm going to apply mains voltage to the transformer with the jumper wire in place across the failed thermal fuse. So long as I don't touch anything, I imagine the very worst thing that could happen is that the filter capacitor could go off with a big bang. I've checked it with the multimeter, and using its low voltage DC test, it doesn't measure short circuit. And I fitted a 1 amp fuse in the mains plug, so that should offer some protection. I will stand back from it for a moment and switch the power on now. Nothing terrible seems to have happened, so let's measure the voltage at the output here. "25 volts RMS, and that's about what I'd expect given that the power supply board needs 22 to 27 volts DC. Here's the thermal fuse. It doesn't look as if it failed due to a simple overheating, but rather the fuse wires have been completely destroyed by a gross overload. Barring someone messing about with this assembly with the power on, which doesn't seem very likely, I can think this only was caused by either a large voltage spike on the mains, or perhaps a bit more likely, the filter capacitor failed with a short circuit, and then the resulting large current flowing through it cleared the short circuit at the same time as this fuse failed. I don't know whether the filter capacitor meets modern safety standards for capacitors used across the mains, although it is marked with the letter X. However, I'll attempt to obtain an appropriate replacement. Also, I don't think I'll be able to find a thermal fuse of this type, but I don't particularly want to operate it without one, so I'll try to find a way of mounting a modern equivalent. I've obtained this small thermal fuse. It's rated to fail should it be called on to pass more than 3 amps or become hotter than 115 degrees centigrade. I don't know how that compares with the original, but I think it should offer a reasonable degree of protection. And importantly, it'll fit in here in the space where the original went. Also, I've disconnected one lead of this mains filter capacitor so I can measure its capacitance. Normally the capacitance of these decreases if they've been damaged. I note it's marked 330 nanofarads. And this meter says it's 390 nanofarads, so I don't think it's sustained any significant damage. It's not gone short circuit and it's passed the power on test, so I'll be reconnecting that for the time being. And finally, I'll fit a new mains cable as this one is extremely dirty. As a final test of the filter capacitor, before reconnecting it, I applied approximately 60 volts DC across it and checked for any leakage current, and I couldn't measure any. So I've reassembled all of these parts and double checked the voltage selector switch is still set to 240 volts. Now this multimeter is connected to the transformer secondary at the output plug, and if I switch the mains on, hopefully we'll see approximately 25 volts RMS as in the previous test. I've verified the oscilloscope will work when powered via the mains transformer, and I now want to turn my attention to the Graticule illumination, which isn't fully working. The front of the CRT can be illuminated by 2 lamps, mounted here and here, and they're attached to this plastic piece, and you can see I've already removed the screws that hold that in place. There's another one of these, but without any lamps, down here at the base of the CRT. The position of these pieces can be adjusted to a small amount, and it's important they be fitted to hold the front of the CRT firmly in position so it can't flop about if the instrument is moved. Now the lamp on the right is still working, but the one on the left has failed. I think it would be possible to find suitable replacements, but if you look closely you can probably see that the heat from these lamps has deformed the plastic, particularly the one on the left, and I don't want to risk this problem becoming any worse, so I'm going to experiment with some LEDs to see whether I can find an arrangement of those that will work well. I've experimented with a few different types and colour of LED, but I've settled on using 4 ultra bright white ones, which produce the effect you can see here. Here's how the 4 series connected LEDs are mounted. Before doing that, I softened this plastic piece using some hot air and was able to bend it back to something more like its original position. I drilled 4 small holes, through each of which is threaded one of the LED's leads, and then I used a generous amount of hot melt glue to hold everything in place. This doesn't look very neat, but it does the job and should be fairly easy to remove if that ever becomes necessary. It also offers some insulation, as the top of this will come very close to the external case once that's put back into position. To make absolutely sure the two can't come into contact, might even fix a piece of this plastic material to the inside of the case above this point. For that demonstration just now, I powered these LEDs using a bench power supply, but now I need to investigate how best to power them from the oscilloscope's own power supply. Here's the original Graticule illumination circuit. I've redrawn it in a manner I think is more sensible than is used in the manual. I've also labelled the colours of the connecting wires. Power supply is taken from the mains transformer secondary and is rectified and filtered but unregulated, or it's taken directly from the external DC input connector. I measured it at 30 volts when generated from the mains, but it'll vary slightly depending on the mains voltage. The manual states an external supply should provide between 22 and 27 volts. The switch is the oscilloscope's front panel rotary power switch, and it's mounted on the rear of the 22 kΩ potentiometer shown here. Note that the mains transformer remains powered even when this switch is off, so it would probably be a good idea to disconnect the mains when the instrument is not in use. It clearly wouldn't be appropriate to simply substitute the LEDs in place of the two parallel connected lamps. For example, once the transistor is fully switched on, the full 30 volts would be applied directly across the LEDs, and that would destroy them. I need to design an alternative control circuit, but one that requires as few as possible wiring changes. Here's the first circuit I considered. I've used a single LED symbol to represent the set of 4 series wired LEDs I've mounted on the plastic bracket. The addition of resistor R1 creates a variable current sink. While the transistor is in its active region, the voltage at its emitter will be about 0.6 volt below that at its base. This sets the voltage across R1, and so determines the current that must flow through it. Assuming the current that flows into the base is small, the current through R1 will be approximately equal to the current that must flow through the LEDs and into the transistor's collector. This current can be varied by turning the potentiometer, and so the brightness of the LEDs is adjusted. However, there is a problem. Even when the control is adjusted to put -30 volts on the transistor's base, making sure it's fully switched off, there is still a circuit through the LEDs and potentiometer. I've tested these LEDs with a 30 volt power supply and 22 kΩ series resistor, and they were surprisingly bright. So this circuit makes it impossible to turn the LEDs off. Here's a small variation that avoids the problem. Now when the transistor is switched off, no current can flow through the LEDs. Sadly, a new problem arises. As with all diodes, the LEDs will not conduct at all if the voltage across them is too low. I measured this series wired set of 4 as requiring about 13 volts once the current exceeded a milliamp. This means the point labelled X will be at approximately -13 volts for almost all of the time the LEDs are illuminated. This voltage varies very little with changes in current. As the potentiometer is rotated from its minimum towards its maximum position, a point will be reached a bit beyond midway, where the emitter will be at -13 volts, and it will then continue to rise towards 0 volts as the control is turned further. In this situation, it's impossible for the transistor to maintain the required voltage at its collector, point X, and so the LEDs will go out. The current flowing into the transistor's base will rise sharply to maintain the expected current through R1, as there will no longer be any current entering the collector. None of this should cause a problem, other than that the brightness control will take the LEDs to their maximum brightness at about halfway, and then switch them off when turned further clockwise. This isn't ideal. Instead, here's the circuit I propose using. It's the same as the previous one, but with a new resistor R2 added to restrict the range of the voltage that can be applied to the transistor's base. Provided this does not exceed the voltage at point X, the LEDs will remain on over the whole range of adjustment, other than when the control is in its extreme anti-clockwise position and the base voltage is within 0.6 volt of the -30 volt supply rail. I've chosen R2 to put point Y at -13.5 volts. I calculated that R1 should be about 650 ohms. Finding its maximum power dissipation would be around 400 milliwatts. It seemed I should use at least a half-watt rated resistor. Not having a wide selection of these, I will use 2 quarter-watt rated resistors in parallel, one of 1 kΩ and the other 1.8 kΩ, to give the 643 ohms shown. The power rating of the 1 kΩ resistor might be slightly exceeded at full brightness, but I don't anticipate using full brightness much, and I can easily change these resistors later if it proves to be a problem. A simple calculation suggests this circuit should give a maximum LED current of 26.6 milliamps. In practice, it'll be less than this, because I did not consider the base current's contribution to the current through R1, nor did I compensate for the fact that the voltage at point Y will fall as the brightness is increased because of the extra base current sourced through R2. The extent of these effects will depend on the DC current gain of the transistor. The BD237 datasheet merely says to expect this to be at least 40. Should it be as low as this, the effect on the voltage at point Y will be considerable, and in that case I'll probably need to change the resistor values. The LEDs are rated to withstand an absolute maximum current of 30 mA, and so this circuit should allow enough safety margin for any modest increase in the supply voltage. With the minimum expected supply of 22 volts, I expect the maximum LED current will be about 10 mA lower, but this should still make the LEDs reasonably bright. All sorts of further improvements could be attempted, for example the use of a low impedance reference to fix the voltage at point Y, and perhaps using one of the oscilloscope's internal regulated supplies to power the whole circuit to avoid changes in response to variations of the external supply voltage. However, I must keep in mind that an accurate, calibrated current sink is not required. I only want to adjust the brightness of some little lights and make as few modifications as possible. So I'll stop at this design and see how well it works. I've modified some of the connections to create the new circuit. The transistor is here mounted on the chassis, and the two resistors that form R1 are clearly visible connected to its emitter. They're linked by this grey wire down here that previously went directly to the emitter over to the lower terminal of the potentiometer, which is connected to the minus 30 volt supply via this short brown wire here that connects to the switch. This blue wire here from the transistor's collector previously went to the upper terminal of the potentiometer, along with another blue wire that went off to one side of the lamps and is now connected to the negative side of the LEDs. I've disconnected both of those from the potentiometer and joined the two together. The join is protected by this piece of black sleeving, so the collector of the transistor is now connected directly to the negative side of the LED string. The base of the transistor remains connected to the wiper of the potentiometer by this black wire down here. That's one that I didn't have to change. The upper terminal of the potentiometer is now connected by this green wire that goes off to the other side of the CRT, where it connects to the 0 volt supply via the new 18 kilo ohm resistor. I've turned the oscilloscope over. Here's the new green wire that we saw just now connected to the potentiometer. It connects to an 18 kilo ohm resistor which is inside this red sleeve, and the other end of that resistor is connected to this white wire which goes off to the 0 volt side of the power supply. This other green wire here simply extends that 0 volt connection so it will reach the positive terminal of the LEDs over here. I haven't connected it yet because I want to carry out a test with an ammeter connected in series with the LEDs. The oscilloscope is switched on, though I haven't turned the control any further than was necessary to do that, and as should be the case, there's no current flowing through the LEDs. I'll now very slowly turn the control clockwise, keeping a close eye on the current to make sure it doesn't reach a level that could damage the LEDs, though I don't expect that to happen. If anything, there could be a problem that the control isn't able to take the current high enough. The LEDs have just turned on. You can see it doesn't take much current to cause that to happen. The controller is now turned fully clockwise, and the LED current is about 22.7 milliamps. So as expected, that's a bit below the predicted 26 or 27. But I think it's reasonable, and the LEDs are glowing quite brightly. At no point during that time did the current start to fall off again, so clearly the control voltage at the transistor's base wasn't taken too high, so that's good. I'll temporarily fit this in place to give a better impression of how it will finally look. And I think that's rather effective. Now, very roughly, I estimated that with the lowest specified power supply voltage of 22 volts, the LED current would be about 10 milliamps less than it is now. So I'll turn it down to around about 12 or 13 milliamps, and let's see how the display looks then. It's noticeably less bright, but still clearly illuminated. I think that's probably going to be good enough. Certainly with the original design, I think the brightness would have varied with the power supply voltage as well. And for comparison, I'll now quickly turn it down to 0, so there's no illumination at all. I'm happy with that. I think I'll leave it on at full brightness for a little while to check there are no problems with anything being overloaded, particularly the power dissipation in the emitter resistors. So that doesn't turn out to be a problem. I think that's that part of the work finished.